Hello, this is my first Khan Academy style video. Right now I'm taking classical and statistical thermodynamics using the book by the same name from Ashley Carter, and I wanted to share with everybody some of the homework that I have to do and how much fun it is. Starting with problem 2-2 in the book, we have a tank of volume 0.5 meters cubed contains oxygen at a pressure of 1.5 times 10 to the 6 pascals and a temperature of 20 degrees Celsius. Assume that all oxygen behaves like an ideal gas, and for certain temperatures it does. The first part of the question A, how many kilomoles of oxygen are in the tank? Well, this right here, if I can pick the right color, I like yellow, obviously. Okay, that's not the right color of yellow. Yeah, I'm very picky, so let's get that color of yellow right there. So now that we have an ideal gas, we know we can use the ideal gas law. PV equals nRT. Okay, so what are they giving us here? Well, first they give you volume, and then they give you pressure, and they even give you temperature. And this is the ideal gas constant, so we have that too. We can just look it up. This right here, this is what we're solving for. This is how many moles. Oops. Technically we want kilomoles, so we will have to use the correct version of the ideal gas constant to give us kilomoles, and we'll do the dimensional analysis to show that this works. So solving for N, we have N is equal to the pressure times the volume over the ideal gas constant times temperature. Okay, let's do a little dimensional analysis real fast, because we know we want N, we want it to equal kilomoles. So if we look at pressure, well, what is a pressure? What does that mean? It's some kind of force, a Newton, over an area. So we have meters cubed. So how much force you have per square meter? That's a definition of a Pascal. And if you ask me, there's a joke about this, but I'm not going to include it in this video. Okay, our volume, well, it says right up here, our volume is 3 meters cubed, so we have meters cubed. Our temperature must be in Kelvin. So how are we going to get N into kilomoles? Well, it has something to do with this ideal gas constant, doesn't it? The ideal gas constant is a joule over Kelvin per Kelvin, a joule per Kelvin times, you guessed it, a kilomole. So what is a joule again? It's nothing more than a Newton times the meter. That gets rid of our meters, gets rid of our force. Our K's cancel out, and all we're left with is a kilomole. So we need R to be in joules per Kelvin per kilomole. That's the specific R that we need to solve our equation for kilomoles. A lot of people just solve for moles, and they use a different form of this constant. Okay, so what do we have? Do we have all of these in the correct units in order for us to get this? Well, our pressure is in pascals, and a pascal was a Newton per meter squared, so we have that. Our volume is in meters cubed, we got that. The only thing I see here is that our temperature was given to us in Celsius. So we have to figure out how do we get Celsius into kelvins. Well, we know a few things about this, right? We know that at negative 273.15 Celsius, we happen to know that equals absolute zero. 0 Kelvin. So if we just add 273.15 to both sides of the equation here, then we can get 0 degrees Celsius is equal to 273.15. Well, this gives us a starting point. We know we want 20 degrees Celsius, so I'm just going to add 20 degrees Celsius to both sides, which gives us our conversion of 20 degrees Celsius is equal to 293.15, not degrees, just Kelvin. So that gives us our last correct dimension to plug into our formula for our temperature. Now I'm going to scroll down and actually do some of the calculations here. So we have, in kilomoles, we have our pressure was 1.5 times 10 to the 6, and let's do our dimensional analysis over here to the side so we get this right, so we can be sure we're at least in the same dimension. So pressure was a Newton per meter squared, and then we're going to multiply by our volume, which was 0.5. Well, let's put it over here. It was meters cubed. This is all being divided by R, which in this case is 8.314 times 10 to the third. This quantity right here gives you the dimensions of joules per Kelvin per kilomole. Okay, and then of course over here we just solved for our 293.15 Kelvin, and there's our Kelvin. Well, what does all this hairy mess over here actually mean? Well, what is a joule? A joule is also defined as 1 joule is defined as a Newton times a meter. So if we just put Newton times a meter, well, we have a Newton up here. These cancel. We have 3 meters. We have meters cubed, and this meter squared times meters. Well, all of these go away. These go away for our Kelvin, and we're left with our correct dimension. So whatever we get, we're at least going to be in the right dimension. Okay, and through the magic of a calculator, this problem ends up being 0.308 kilomoles. Alright, there's our answer. And I'll post another video with part B.